Imagine a ribbon of concrete stretching for 38 kilometers, suspended over an endless expanse of water. No solid ground to anchor it, just the vast, indifferent lake. This monumental undertaking, against all odds, nearly never saw the light of day. This is the story of what would become the world's longest bridge over open, navigable water. A record-breaking marvel completed in 1956. In an era devoid of satellite navigation, computer modeling, or even a comprehensive blueprint, these engineers faced not just one, but a cascade of unprecedented challenges. One problem in particular had no known solution. They weren't merely constructing a bridge, they were inventing the very methodology for its creation, pioneering new techniques right there on the unforgiving waters of the lake itself. Even before the first steel pile could kiss the water, a fundamental crisis emerged. The lake bottom, a treacherous layer of soft organic mud 30 feet deep, offered virtually zero bearing capacity. It was a liquid grave, capable of swallowing a pile driver whole. Every depth sounding, every critical measurement, meticulously recorded by hand in a notebook. No satellites to guide them, no advanced sensors to warn them. Just raw geometry, human grit, and unwavering precision. With a single audacious design, one colossal lake to conquer, and a relentless deadline of just 14 months, the stakes were impossibly high. Lake Pontchartrain, a vast inland sea spanning 630 square kilometers. When storms descended, its waters churned with the fury of a small, untamed ocean. This is the epic saga of the visionaries who defied nature, engineered the impossible, and forged a structure that stands unwavering 7 decades later. By 1950, the vibrant pulse of New Orleans demanded expansion. Yet, accessing the burgeoning North Shore communities meant a 90-minute odyssey around the lake. 40,000 families, tethered to the city, endured a 2-hour round-trip commute daily, a burden too heavy to sustain. Engineers of the era understood river bridges. Narrow, often anchored to solid banks, their currents predictable. A lake, by stark contrast, offered none of these reassurances. It was wide, bottomless, and utterly capricious. Then, in 1952, the first soil boring samples returned. Their implications were so dire, they brought the entire project to a grinding halt for nearly a full year. The organic lake sediment, a treacherous mixture, compressed under any load, shifting unpredictably with the slightest vibration. Driving a pile into it was akin to plunging a column into cold, viscous porridge. Every subsequent boring sample echoed the same chilling truth. This layer of unstable mud wasn't isolated. It stretched for miles in every direction. This was not mere earth. It was decomposed vegetation accumulated over thousands of years, a geological memory of ancient swamps. Under-pressure piles didn't merely sink. Some were utterly consumed, vanishing into the abyssal mud in less than 60 seconds. A chilling, silent disappearance. Precious equipment was lost to the lake's insatiable depths. Time, a luxury they couldn't afford, slipped away, and with every grim boring report, the projected costs spiraled ever higher. Then, the lake unveiled its final, insidious secret, one for which no budget or contingency had been made: fog. A total, disorienting whiteout that could descend without warning, engulfing everything. A barge crew, adrift in this mid-lake spectral shroud, found themselves without reference. No land, no sound, nothing but a trembling compass to guide them. Navigation became a terrifying act of faith, positioning a perilous estimation. A single miscalculation in this opaque void meant driving a critical pile in the wrong place, condemning weeks of work, or worse, compromising the entire structure. It was into this maelstrom of challenges that the Louisiana Bridge Commission brought in the formidable expertise of Majeski and Masters, men who understood that sometimes, to build the future, you must first invent it. In the mid-20th century, a monumental vision took shape: to span an impossible expanse of water, connecting distant shores with a ribbon of steel and concrete. To achieve this, the project turned to one of the nation's most venerable bridge engineering firms, a titan forged in the crucible of countless structural triumphs. Their reputation was unblemished, their expertise undisputed. Authorization for this audacious undertaking arrived in 1953. It was more than a simple permit, it was a mandate, a declaration of intent to conquer the seemingly unconquerable. The financial backing was equally staggering. A budget of $30 million, an astronomical sum for the era, underscoring the sheer scale and profound importance of the endeavor. The deadline, though never explicitly stated, was etched into every blueprint, every calculation, every anxious glance across the vast, shimmering lake. It was a silent, unyielding pressure, a constant hum beneath the roar of ambition. The South Shore construction yard, a sprawling expanse of newly cleared land, sprang to life. Here, on solid ground, every single component of the future bridge would begin its existence. This was the birthplace of a marvel, a meticulously organized factory where raw materials would be transformed into precision-engineered giants. The design team, facing unprecedented challenges, made a pivotal decision, one that would fundamentally alter the course of construction and redefine conventional wisdom. Precast the piles on land. This was a radical departure from established practice. There would be no wet concrete poured into open water, battling currents and unpredictable conditions. Instead, each pile would be meticulously cast on shore, allowed to cure to its maximum strength in a controlled environment, then carefully floated out to its precise position on a dedicated supply barge. These were not minor elements. Each pile measured a formidable 16 inches square and stretched an imposing 54 feet long. Within their concrete hearts lay a complex web of stress reinforcement, engineered to withstand the relentless forces of the lake, and the sheer quantity required was staggering. Exactly 9,500 of these colossal pillars would be needed to anchor the bridge into the lakebed. Separately, massive concrete collars, known as pile caps, were cast. These were not mere adornments. They were critical structural components, designed with uncompromising precision to transfer the immense beam load directly into the top of each embedded pile. Before any pile was deemed fit for its watery grave, it underwent a rigorous physical inspection. Every inch scrutinized for flaws, every dimension verified. Only then was it permitted to leave the safety of land. The logistics were a ballet of synchronized power. Supply runs were continuous, a relentless procession across the lake. Barges moved in convoy, laden with their precious cargo, a constant pulse of concrete and steel feeding the ever-advancing construction front. At the heart of this operation was the custom-built pile-driving barge, a marvel of specialized engineering. Its shallow draft, a mere 1 meter, allowed it to navigate the lake's notoriously variable bottom depths, reaching areas where conventional vessels dared not venture. Yet, even with such sophisticated tools, nature presented its own formidable obstacles. The pile had to enter the soft, silty mud at an absolutely precise angle. A deviation of even 2 degrees, a seemingly minor tilt, would prove catastrophic. The massive pile cap, designed to see perfectly, would simply not align with the beam, rendering the entire section unstable. When the hammer dropped, its colossal weight intended to drive the pile downward, an unexpected resistance emerged. The mud, instead of accepting the pile, began to rotate it, twisting it off its intended axis. It was a silent, frustrating battle against an unseen enemy. The guide frames, designed to ensure perfect alignment, became the first casualties of this unforeseen challenge. They were redesigned, then redesigned again, twice, directly on site. What had worked flawlessly during testing on land, where conditions were controlled and predictable, failed spectacularly when the barge itself flexed and swayed in the lake's relentless swell. Each blow of the hammer, each agonizing inch of progress, was meticulously measured. Engineers tracked how far the pile moved with every drop, logging every detail. Piles that angled uncontrollably in the soft upper mud were sometimes pulled from the depths, a monumental effort in itself, and then re-driven, costing precious hours per pile. And in a project of this magnitude, every single hour mattered. Every minute was a calculated expenditure against an unyielding deadline. The fundamental task of each pile was deceptively simple: punch through the yielding, soft mud and seat firmly into the stiff, unyielding clay layer lying 50 feet below the surface. That dense clay, a geological anchor, was the only true foundation, the bedrock upon which the entire bridge would ultimately rest. It was the bearing layer, the final, critical point of contact with the Earth's enduring strength. Yet, even this foundational layer presented its own unique set of problems. Each pile, it seemed, was its own isolated crisis. The depth of the mud varied wildly across the lake bed. The resistance encountered by the driving hammer was never consistent. Nothing about this vast, ancient lake was ever predictable, ever uniform. It was a living, breathing entity, constantly shifting, constantly challenging the meticulously planned human endeavor. Despite these Herculean struggles, by early 1955, the pile line was advancing with remarkable speed, relentlessly pushing into the lake's heart. They were averaging the completion of one full span every 2.5 days, a testament to the ingenuity and sheer persistence of the crews. Once the piles were driven and securely capsty-foot sections across each row of piles, each of these precast beams weighed an astonishing 60 tons, and their placement tolerance was a mere half an inch in open water, a feat of precision that defied the very forces of nature. Grout, a specially formulated concrete mixture, was then meticulously injected, permanently locking the beam to its cap. An improperly filled joint, even the smallest void, meant movement under the constant stress of traffic. And movement, however slight, was an invitation to fatigue failure, a catastrophic structural collapse waiting to happen. To accelerate the relentless pace and cut critical supply times, another innovative solution emerged. A floating precast yard. A self-contained factory was established directly in the middle of the lake, bringing the manufacturing closer to the point of installation, a testament to an unwavering commitment to overcome every obstacle, to build the impossible. The core challenge was foundational. Concrete itself, a material of terrestrial solidity, had to be mixed, formed, and cured not on stable ground, but upon the ceaseless, shifting surface of the water. Engineers poured massive quantities of the liquid stone onto barges that never truly held still. Even the gentlest swell, an almost imperceptible ripple on the vast expanse, subtly distorted the precise angle of every single formwork. Each pour became a delicate negotiation with the lake's relentless motion, a constant battle against the very medium meant to support the structure. There was no solid ground for a lunch break, no momentary escape from the rocking deck. Workers lived for weeks on vessels, their temporary homes adrift in a world defined by its liquid boundaries. Mid-Lake became an isolated universe, a place with no easy exit, no familiar road leading to a town, no comforting sight of a hospital on the horizon. If a crisis unfolded, if an accident struck, if a man fell ill in that vast, shimmering emptiness, immediate help was not minutes, but hours away. The sheer scale of the isolation was a silent, ever-present pressure, a constant reminder of their precarious existence. Yet, with each completed deck section, a new platform emerged, a solid anchor point for the next segment. The bridge, in an almost organic fashion, built itself forward, extending a steel and concrete spine across the water. The sun, reflecting off the lake's surface and the fresh concrete, created an oppressive heat and a blinding glare that disoriented even the most seasoned crew. This relentless assault of light and warmth, combined with the constant motion, made every 10-day rotation off Mid-Lake a desperate scramble for solid ground and a moment of respite. Night shifts, when the lake was calm and the air cooler, became a precious window for uninterrupted progress. Work only ceased when the wind, rising from the horizon, rendered the massive cranes too dangerous to operate, forcing a temporary surrender to nature's power. This colossal endeavor stretched over 24 kilometers, a monumental undertaking completed in just 14 months. That translates to an astonishing 58 meters of finished bridge every single day, across open water, utilizing the engineering equipment and techniques available in the 1950s. By the middle of 1955, the southern half of this audacious span was declared complete. Simultaneously, a crew on the North Shore, starting from Mandeville, was advancing steadily, meticulously laying down their own sections, driving towards the eventual meeting point. The two fronts, pushing relentlessly from opposite ends, had to converge with absolute, uncompromising precision. A mere single degree of error at the project's inception, a fractional miscalculation in the initial alignment, would have resulted in a permanent, unforgivable misalignment, a visible flaw stretching for miles across the lake. Their solution relied on optical triangulation, a painstaking process of measuring angles to fixed monuments on the distant shores. It was pure geometry, executed by hand, calculated with slide rules and unwavering focus. And, against all odds, it worked. The two halves met, seamlessly, perfectly, a testament to human ingenuity and meticulous planning. Beyond its sheer length, the bridge boasted another crucial feature: a drawspan designed to provide 8 meters of vertical clearance for sailing vessels navigating the lake. The hinge mechanism, a complex piece of engineering nicknamed the basketball hinge, faced an unrelenting adversary in the form of salt air and the pervasive humidity of the Louisiana climate. It had to endure for decades, without a single point of failure, a testament to its robust design. Remarkably, it still performs its vital function today, a silent guardian of both passage and structural integrity. With the main structure complete, the intricate details began to fall into place. Handrails, expansion joints, and the final road surface were all fitted section by section, meticulously attached to the completed pile cap grid. The expansion joints, more than mere gaps in the pavement, were critical components, allowing the massive concrete structure to flex and breathe with the dramatic temperature swings of the region. They acted as the bridge's pressure relief valves, absorbing the immense stresses of thermal expansion and contraction, preventing cracks and structural fatigue. In June of 1956, the southbound span officially opened to the public. The journey across, a mere 23 minutes, immediately shattered records. On that inaugural day, drivers, awestruck and perhaps a little apprehensive, slowed their vehicles to a crawl. Some even stopped entirely, momentarily paralyzed by the sheer novelty of the experience. They had never before driven over such a vast expanse of open water, the horizon seemingly dissolving into the distant sky. Guinness World Records swiftly confirmed the achievement, the world's longest bridge over water. It was a title Louisiana would proudly hold for many decades. The initial toll was 93 cents. For many families in 1956, this was a significant sum, often close to an hour's wages. Yet, the bridge fundamentally changed the daily calculus of life, dramatically shortening commutes and connecting communities in unprecedented ways. However, this marvel of engineering also presented an unexpected psychological challenge. Some drivers, halfway across the vast structure, were overcome by panic attacks. The flat, uninterrupted expanse of water on both sides, combined with the bare concrete deck, created an eerie optical illusion, a sensation of driving directly into an open, boundless sky. There were no shoulders, no comforting median, just two narrow lanes, barely enough room to pull over if something went wrong, amplifying the sense of vulnerability. Within 3 short years, the relentless assault of the salt air began its insidious work. Chloride intrusion, a slow, patient, and utterly relentless process, started to attack the very concrete itself. While the original engineers had painstakingly calculated wind loads by hand, a feat of immense computational effort for their time, no one had accounted for the catastrophic scenario of a direct hurricane hit. That oversight would prove devastating. In September of 1965, Hurricane Betsy, a monstrous force of nature, made landfall. Its terrifying winds slammed into the causeway, exceeding 120 miles per hour for 6 agonizing hours. The structural integrity of the bridge was tested to its absolute limit, resulting in 17 spans suffering catastrophic damage. The bridge, a monument to human ambition and engineering prowess, had faced its ultimate adversary. Its initial triumph, a testament to overcoming the water, now confronted the raw, unbridled power of the atmosphere. The story of its construction was one of conquering the impossible, but its ongoing existence would become a continuous saga of adaptation, resilience, and the relentless fight against the elements. The colossal deck sections lay violently displaced, a testament to nature's raw, unbridled power. The massive drawspan, a structure designed for precision and function, had been ripped from its very seat, left twisted and broken. Hurricane Betsy had passed, leaving behind a scene of devastation that defied the very principles of engineering. Within 48 hours, a team of engineers, grim-faced and determined, descended upon the site. The air hung heavy with the scent of salt and wreckage. What they meticulously documented in the hurricane's chilling aftermath would not merely influence, it would fundamentally rewrite every single specification for the future northbound span. Their findings were a stark, undeniable lesson etched in bent steel and shattered concrete. The foundational piles, driven deep into the lakebed, had held firm against the storm's fury. The robust caps, designed to distribute immense loads, had also endured. But the critical question lingered, a chilling whisper amidst the debris. What, then, had truly failed? The answer was both deceptively simple and horrifyingly profound: the beam-to-cap connections. The colossal concrete beams carrying the weight of the roadway had simply slid off their moorings, dislodged with an almost casual ease by the storm's relentless surge. A vulnerability had been exposed, a silent flaw in the very heart of the structure. Hurricane Betsy delivered one undeniable, brutal lesson. Every single connection, every point where concrete met steel, had to be rendered inseparable. An immense retrofitting operation began, a race against time and the elements. Each beam tie was meticulously resecured, welded down with an unwavering resolve, before the southbound span could ever safely reopen to the public. The scars left by Betsy were not merely repaired, they became the unyielding blueprint for the northbound span's very existence. Every single point of failure, every weakness revealed by the hurricane, transformed into an absolute, non-negotiable requirement for reinforcement. From the outside, the second bridge, rising alongside its predecessor, would appear almost identical. A casual observer would detect little difference, yet beneath the surface, hidden from plain sight, the fundamental structural connections within were radically, profoundly different from the original design. This was a bridge born of hard-won experience, a monument to resilience and adaptive engineering. Construction of the northbound span commenced in 1967, a monumental undertaking that embodied the lessons of the past. Pile spacing was significantly tightened, creating a denser, more resilient foundation against future forces. The new pile caps were innovatively designed, with sturdy steel dowels protruding from their surfaces. The concrete beams, rather than simply resting upon them, were then cast directly around these dowels, forging a single, monolithic connection. No more simple sliding. This was an unbreakable bond. The width of these caps was also subtly increased by 14 centimeters. A seemingly minor adjustment, perhaps, but one that would prove to be a major, life-saving difference when another 12-foot storm surge inevitably arrived. For 2 arduous years, the southbound span continued its vital work, carrying the relentless flow of traffic, while its colossal twin slowly, methodically rose beside it. 2 colossal bridges under construction simultaneously, a testament to ambition and necessity. By 1969, a revolutionary technology had emerged: laser alignment. The northbound span proudly stood among the very first water bridges in the United States to harness the unparalleled precision of laser positioning. Laser transit offered millimeter accuracy across distances exceeding 3 kilometers, transforming the art of large-scale construction. The northbound beams themselves underwent a radical redesign, engineered for longer, clearer spans. This innovation allowed for fewer piles per kilometer, optimizing material use, while simultaneously enabling the bridge to carry significantly higher load ratings. The very road surface received a crucial upgrade, transitioning from bare, unforgiving concrete to a textured aggregate. This vital change provided dramatically better grip, a critical safety enhancement in the treacherous conditions of rain and the notorious Lake Pontchartrain fog. The final northbound pile, one of over 4,700 additional piles driven into the lakebed, was meticulously positioned in 1968. A year later, in 1969, the northbound span triumphantly opened, instantly doubling the causeway's capacity with its 4 new lanes. The impact was immediate and profound. Within a single decade, the North Shore population of St. Tammany Parish doubled. The bridge, a silent steel and concrete leviathan, had almost single-handedly reshaped the economic and social landscape of an entire region. Yet, even with its newfound strength, the lake presented its own unique, insidious challenge: radiation fog. Lake Pontchartrain is infamous for producing this dense, disorienting phenomenon with almost zero warning. The chilling embrace of cold air meeting warm, moist air can plunge visibility to near zero in a matter of minutes. To combat this ever-present threat, highly sensitive visibility sensors are now strategically mounted every mile along the entirety of the 38-kilometer span. A sophisticated control center constantly monitors every single sector simultaneously, a vigilant eye across the vast expanse. When visibility drops below 200 feet, the bridge closes. This threshold, a non-negotiable safety parameter, has never once been adjusted, a testament to its unwavering importance. When the gates swing shut, traffic backs up for miles, a frustrating yet necessary inconvenience. The bridge reopens only when every single zone clears simultaneously, ensuring absolute safety for every traveler. For decades, every single crossing was meticulously logged, a manual testament to human diligence. The revenue generated from these tolls did more than just cover costs. It directly funded the critical, relentless maintenance required to preserve this colossal structure. From its very first day, the bridge paid for itself, a self-sustaining marvel of engineering. The ceaseless assault of salt, the insidious accumulation of sediment, the relentless battering of debris. Marine maintenance is not merely an option. It is a fundamental, existential requirement. It is the unwavering commitment to this constant vigilance that ensures the bridge still stands today. Every few years, in the cold, dark embrace of the lake's depths, highly trained divers descend to meticulously inspect every single submerged pile, each one a silent sentinel against the relentless forces of nature. Their work, unseen and often unheralded, is a vital part of the continuous, never-ending battle to preserve this monumental achievement. Beneath the relentless sun and the constant spray of Lake Pontchartrain, a quiet war is waged. Teams of engineers meticulously scan every inch of the bridge's colossal structure, searching for the telltale signs of fatigue: spalling, hairline cracks, and the glint of exposed rebar. These are the insidious entry points. Through these microscopic fissures, chloride, carried by the very air and water, penetrates deep into the concrete, reaching the steel tendons within. There, it begins its silent, destructive work, corroding the rebar from the inside. Left unchecked, this internal decay becomes a powerful, splitting force, tearing the concrete apart from its core. The battle against this relentless assault is fought year-round, without pause. Damaged piles are not simply patched. They undergo a precise, multi-stage restoration. First, a specialized epoxy is injected, sealing the wounds and reinforcing the weakened concrete. Then, a fiber-reinforced polymer wrap is applied, creating a new, resilient skin that binds the structure and prevents further ingress. It is a testament to this unwavering commitment that in 70 years of continuous service, not a single span section of this monumental structure has ever required replacement. The diligent, unending repair has always been enough. Even the original railings, installed in 1956, continue their duty. 70 years old, marine-coated, and still fully compliant with modern safety standards. They stand as silent sentinels, defying the passage of time. Every morning, between 8 and 9 o'clock, the bridge experiences its peak flow, a southbound deluge of vehicles. Yet this vital artery effortlessly manages traffic in both directions simultaneously, a constant, pulsating flow of life and commerce across the vast expanse of the lake. Then came August of 2005. Hurricane Katrina, a name now etched into history, made landfall as a Category 3 storm. The sheer, terrifying power of the hurricane unleashed an unprecedented surge upon Lake Pontchartrain, pushing its waters 12 feet above their normal level. The entire north shore of the lake vanished beneath the deluge. Mandeville, Covington, Lacombe, communities were utterly submerged. Both approach ramps leading to the causeway, at either end, disappeared beneath the rising tide. Yet, with an almost defiant grace, the main bridge structure itself remained above the surge. 3 days later, as the immediate fury subsided, a team of engineers navigating through the devastated landscape by boat finally reached the causeway. What they discovered there, amidst the widespread destruction, left everyone stunned. A distinct line, visible along the bridge's supports, marked the terrifying high watermark of the lake during Katrina. The bridge deck, at that point, had been under 2 feet of churning surge water, its surface coated in a thick, unsettling layer of mud and debris. But below that chaos, the structural integrity was absolute. There was 0 structural damage. Every pile cap remained perfectly seated. Every beam was locked firmly in place, all holding. An example is found to be securely seated, every beam tied. The causeway, against all odds, reopened to emergency traffic within an astonishing 3 weeks. It became the very first road link, the sole lifeline, restored into New Orleans after the storm's devastation. Without its steadfast presence, rescue convoys would have been forced to navigate hours longer through treacherous, flooded surface routes. Precious time that people, trapped and desperate, simply did not have. Thousands, driven by necessity, walked out of the city across its deck for days, a purpose it was never designed for. Yet it held, unwavering. In the harrowing aerial footage of the aftermath, the causeway stood as the only dry road, a solitary, undeniable connection to the besieged city. It was, in that moment, everything. The approach ramps, being land-based, took longer to clear, having borne the brunt of Katrina's initial impact more severely than the open spans. Yet the original 1956 piles, the very foundation of the causeway, showed 0 structural compromise. The Louisiana Department of Transportation and Development declared Katrina a complete and unequivocal design validation. The engineers of 1955, working without the aid of computers, their calculations based on raw intellect and deep understanding, had been right about every single detail. Every lesson learned, every connection made, every design decision, all of it survived Katrina. Today, 42,000 vehicles traverse the Lake Pontchartrain Causeway daily, a continuous stream of life. It never closes for scheduled maintenance. The Greater New Orleans Expressway Commission operates this behemoth, with a dedicated staff of 250 working 24 hours a day, 7 days a week. Maintenance is conducted under live traffic, a logistical ballet of precision. Lane closures are planned down to the minute, ensuring that the critical flow of traffic continues uninterrupted, even during the most demanding peak hours. This bridge, a testament to human ingenuity and relentless upkeep, stands as a permanent, living monument to resilience, silently carrying the weight of a city's history and its future, just as it has for 70 years. And just as it will for decades more. Across the vast, shimmering expanse of Lake Pontchartrain, 2 distinct worlds once stood apart. The South Shore, bustling Metairie in Jefferson Parish, the North Shore, the tranquil haven of Mandeville, nestled within St. Tammany Parish. Between them, a formidable 23 miles of open water, an imposing barrier that demanded an audacious solution. A bridge. At the precise midpoint, mile 12, the experience is profound. No land is visible in any direction, a perfect, unbroken circle of water meeting sky. This is the most complete open water exposure found in American highway driving, a deliberate isolation designed to conquer distance. To maintain this colossal structure, every mile marker and every single road marking is meticulously repainted on a rigorous 3-year cycle. The same dedicated crews rotate through the full length of the bridge, their work a constant, silent testament to its enduring presence. In 2011, China's Jiaozhou Bay Bridge claimed the global length record. Yet, its path crosses primarily over viaducts, not the deep, open, navigable waters that define Lake Pontchartrain. The Guinness World Record classification remains resolute. The longest bridge over open, navigable water. This distinction is vital, for the challenges of building across such a dynamic, unpredictable environment are vastly different. Every long-span water crossing constructed after 1956, from the grandest suspension bridges to the most intricate cable-stayed designs, borrowed techniques, innovations, and hard-won lessons from the engineers who dared to build across this very lake. Every single one of them. Emmett Harrington, the visionary director of this monumental project, stepped into his role as an administrator. He emerged, forever transformed, as a builder. His legacy endures, not just in the steel and concrete, but in the very fabric of modern infrastructure. The original South End Toll House, a concrete footnote to history, was carefully preserved when electronic tolling replaced its human operators in 2014. It stands, a quiet sentinel, marking the passage of time and technology. Today, modern acoustic testing confirms the structural integrity of every pile, a marvel performed without the need for excavation or dangerous underwater diving. Sound waves are sent traveling through the 70-year-old precast concrete, submerged in a saltwater lake, and they return with the truth. The signal comes back clean, every single time they test it. This is the stark reality of engineering without a safety net. No computers to model complex stresses, no GPS for pinpoint accuracy, no luxury of a second design phase. 14 months of relentless construction with no second chance, no room for error. 38.6 kilometers, 2 distinct spans, 9,500 piles driven deep into the lake bed. 70 years have passed since its completion, and not one structural failure has ever been recorded. It stands unyielding. What truly resonates is the profound uncertainty that hung over its creators. They did not know for certain it would work. The lake offered no precedent, no prior blueprint for such an undertaking. They built it anyway. And it held. The men who poured their lives into this colossal endeavor are mostly gone now, their hands and minds faded into history. Yet their work endures, silently carrying 42,000 vehicles across this lake every single day. The initial costs, $46.8 million for the south span, an additional $30 million for the north. Today, its value is incalculable, a cornerstone of regional commerce and daily life. Those first drivers, venturing across this unprecedented structure, had no idea they were traversing the most technically original bridge in the entire history of American infrastructure. Today's drivers cross in a mere 20 minutes, often without a second thought. That quiet, almost mundane acceptance is the exact measure of how completely, how brilliantly, the engineering succeeded. This bridge was built by men who trusted their mathematics more than they feared the immense, unpredictable power of the lake. And in 70 years, the lake has never once proved them wrong.